Yeah, dear students, today we'll discuss balance binary search trees further left in our syllabus. Okay, starting with Splay trees. Can you able to see my screen? Yes. Splay trees, basically, it's again a kind of balanced binary search tree. Some of the balanced binary search trees we have already seen in previous couple of classes, like AVL tree, and V trees. In similar line, you can probably find here splay trees. Uh, it's a very similar to that what we have discussed before. It's basically a binary search tree. So the properties of binary search trees are quite applicable to even split trees as well here. If you look at the time complexity, while performing any operation over it is around logarithmic here. Uh, Balance trees require an extra piece of balancing information. Balance trees have expensive insertion and deletion, but split trees takes advantage of 90-10 rule actually. So we'll see what is that exactly. Here we can have two type of them rather bottom up and up top down kind. So now if you look at here while you are performing the operation um, on the split trees, whether it could be searching, insertion, or deletion, right? There are three different cases you may fall with. One is zigzag, and zig zig. Okay, I hope you can probably see here. Zig, zigzag, and Zig Zig. These are the three different cases you probably fall with. So basically, X is the currently accessed node. The recently accessed node is what being here pointed through X, right? And from this particular point of view, we're going to uh, identify our tree under these three different cases: zig, zigzag, and zigzag. Basically, when you are performing any operation on binary search tree, you will be taking a traversal right from the root onwards. Okay, but then when you insert a certain node, probably in the left or right, so the last node which you access after you perform that operation, rather, right? So that particular node is what's said to be the X here, rather, right? So from this X point of view, we will see our tree is falling either under zig situation or zigzag situation or zigzag situation. So considering these three situations, we are applying the appropriate mechanism in order to bring back into the balanced binary search tree. This is what exactly the split tree mechanism is. Rather, we can probably going ahead with we'll see how what exactly the zig, as I said, x when x is a non-root and p is the root, right? P is the root. It means you can see here, this is the zig situation. X is the node which you have recently accessed, and whose parent is p, let us say. Okay, X is the one which you have accessed, nothing but a non-root, and its parent is the root node, rather, right? So this particular situation is said to be the zig situation. So in this situation, the kind of mechanism, the solution you're going to apply is nothing but a single rotation. That is, the in this case it is going to be right rotation, because your X is at the left of your parent, right? So then you're going to apply the right rotation. If your X is at the right of your parent, then you apply the left rotation. So when you apply the right rotation here, you can see X will occupy the root, and this right of X will go to the left of P, and P will come to the left of X. Okay, this is how exactly the right rotation is going to be applied on this particular tree when it is in zig situation. There is another situation which we talked about is nothing but the zigzag situation, right? So this is you are going to encounter with when your node, the recently accessed node X, has a parent P and a grandparent G. There are two, parents. There is a parent and there is a further grandparent you have for, let us say, X. But then when X is at the right child of the parent, then parent is at the left of its grand. Okay, Understand. So it means when they are at the different positions. This is how the zigzag situation is. The let us say they recently access node is nothing but X, from where you are going to find whether you are in a zigzag situation. I am saying this is your zigzag situation because if you see for your X you have a parent node and you have a grandparent node rather, right? And you can see the X is connected to the right of its parent, whereas the parent is connected to the left of its grandparent, right? Or vice versa. If let us say X is at the left of its grandparent and parent is at the right of its grandparent, that could be this kind of situation, rather, right? Okay. So either this situation or this situation. These are the situations are said to be what zigzag situation. So in this you're going to have double rotation. Okay, you'll be having double rotation. First you will be applying for example, if you take this particular situation, you will first apply a rotation on its parent, that is left rotation, and then you apply the right rotation, okay, on its grandparent in order to bring X onto the root, right? The node which is currently accessed is required to be splayed. Splaying is nothing but bringing that particular node onto the root is what exactly the splaying is. What do you mean by splaying? Splaying is something like bringing that node onto the root node. As you can see, after I apply these two rotations, I got the X onto the root. Yes or no? So this is what exactly this playing is rather, right? So even in this situation, what you do, you will apply two rotations, right? One is right rotation here, and then you will apply the left rotation here, right? Then you can see X will occupy the root position. X is a node which is recently accessed on your binary search tree when you perform any operation, whether it could be search, insert, or delete. But now, after you perform any of the operation, it could be search, insert, or delete, that recently accessed node, which is nothing but X, we are saying, is required to be splayed. It means it has to be bring onto the root node. So first you need to identify under which particular situation you are, right. From the X point of view. If you are in zig position, you will apply single rotation. If it is zigzag position, you apply double rotation like this. And there is another case you have is nothing but the zig zig, right? This is said to be zig zig. And this zig zig is going to be occur when X is X and its parent both are on the same side, either on the left side or the right side of its parents, right? X is at the left of its parent and parent is also is at the left of its grandparent. In that situation, you say it is zig zig, right? So you can see this is zig zig. You can see here wherein X is at the left of its parent and its parent is also left of its grandparent, or I vice versa in the sense that you could be having this kind of situation rather, right? That is, X is on the right and its parent is also on the right. Either this could be or that could be. In both the situations, you say it is zig zig. In that also, you will be applying double rotations. That is, here you are applying one rotation on its parent, that is right rotation. Again, you apply a right rotation, two right rotation. Similarly, here also two left rotation. Fine. So that your X has to be brought onto the root. This is what exactly the motive behind, right? The currently or recently accessed node after the operation, which is considered to be X here, to be brought onto the root. So while bringing onto the root, by identifying that X from X point of view, your tree is under which particular case, whether it is zigzag or zigzag. So taking these all three different situations, you will apply the appropriate rotation in order to bring back into the you know balanced binary search tree. This is what exactly the motive behind applying this splay operation, right? After every insert, delete, or such kind of thing. So looking at this particular skew tree, you can see this is skew tree. This is falling under zigzag, right? This is falling under zigzag. So what happens here? The recently accessed node, let us say for example X, then this one has to be brought onto the root. Okay, if you have inserted the nodes like this, okay, 7 6 5 4 3 2 1, this is the order in which if you have tried to insert the elements, what happens? 7 will become the root, then 6 go to its left, and 5 goes to its left, like that further until you reach 1. Now the recently accessed node, let us say, is 1. Then this has to be brought onto the root node. Okay. So how do we do that? Identifying, considering this x, from x point of view, what is this situation, under which particular you are under zig zig situation. Zig zig means your the x is having parent, and its parent is also having a parent, that is grandparent, right? And both parent and grandparent are, and its you can see x and parent, both of them are at the left of their parents rather, right? So this particular situation is said to be zig zig. In this zig zig situation, what do? You apply two rotations, right? Right on parent, and then right again on stand parent, right? Then you get the tree like this. Again, this is your x. Now you can see your parent is this, and this is your grandparent. And now you can see it is again zig zig. And again zig zig, what do? You apply two rotations. Here this left rotation, right rotation, here again right rotation. So when you do that, you get your one, like one here rather, right? Then again you can see you have parent and grandparent. This is again a zig zig situation. Then again you will apply double rotation, that is right on its parent and right on its grandparent. Then you will get your one on its root. So bringing that recently accessed node, this is nothing but one to bring onto the root, is what exactly you are trying to do. By identifying that under which particular case you are falling with, applying the appropriate rotations accordingly, you will make the tree into the balanced kind. So I hope this is clear to you, all of you. So that this is what exactly you do in splay trees, right? A splay operation is performed after every access to a node, as I said, right? Finding, you are finding a node, splay the tree after finding it. Once you perform searching operation, finding operation, what you have to do? You have to splay the tree again. It means the recently accessed node has to be brought onto the root, right? The node which you have rather searched is nothing but the x rather. So that x has to be brought onto the root. If you are trying to delete min is simple. Perform the find min, you can do, and then that has to be bring on to the top, that is root, right? So that becomes the new root, right? And when you are trying to remove any node from the split trees, access the node which makes it the root, that delete which gives two trees. Like you can see with an example here how you perform a removal operation. For example, you want to remove, let us say, 6 here, right? You want to remove 6. So what do? First you search for 6. Before you delete, you need to search whether it is available or not. Only then you can go for delete rather, right? So you have perform a search operation. When you perform the search operation, this is a recently accessed node, that is x. Then it has to be brought onto the root, right? It has to be brought onto the root. Once it is brought onto the root, then this has to be deleted. So when you delete, you get two trees, right? Left side one tree left, and right side another tree. Then you will find the maximum out of its left child, right? That is what exactly is said here. Find the max of the left, right? Find the max of the left tree, and that is the new root, right? So you can see here what is the max of the left, which is nothing but 5. So this 5 becomes the new root. Then the 7 goes to the right of the same. This is how the tree becomes after you delete 6. This is how you perform the delete operation on the split trees. I hope I am clear. Yeah, this is how you perform the insert operation. You can see while you are performing this insert operation, if you fall with zig case or zigzag or zig case, you will have to apply the appropriate rotations and then splay it. Fine. And finding the was searching. How do you perform a searching operation that I have shown you here? Before deleting, you for example, you want to delete 6. Before deleting also you need to perform a search operation. So you have perform the search operation. Once you perform the search operation, that node which you have found has to be brought onto the root. Okay, so that has been brought here onto the root by applying the required rotation. This is coming under which particular situation? It is coming under zig situation, right? It is having the node which is currently axis x, which is at the right of its parent, right? Which is right. This is a non-root and its parent is a root. Then in that case, you will be applying a single rotation. This is said to be zig situation. Yes or no? It's going to be zig situation. So you will be applying the right rotation, sorry, left rotation here. So when you apply a left rotation, what happens? This 5 goes to the right of 4 and 4 comes to the left of 6 and 6 will occupy the root position. So exactly. So after 6 is brought onto the root, then you will delete 6. Removal operation. What do you do in removal operation? First you find the node. First you need to search for the node to be deleted. So once you found the search operation and it is found that particular node is available, then what do? You will try to you will bring that particular node onto the root, right? That is what you have done here. Then what you are going to do, you will be deleting. By deleting that root node, that tree will be divided into two. So you will find the max of the left, that will make the that will become the root, and this right will go and get attached to that particular currently available root node, rather, right? That's how exactly the removal operation is done. I hope this is clear to all of you. Yes, any doubt here? Shall we move on to the next topic? Yes, please. Am I audible? Please, one of you respond.
Yes, sir, audible.
Yes.
Audible, sir.
Yeah. Is it clear? The concept is clear to all of you? Yes.
No,
Shall we move on to the next?